All right, in this video, we are beginning section 3.2, and we're going to focus on some different properties of polynomial functions. I'll do two videos for this section. This one's going to focus primarily on the end behavior of a polynomial function. Okay, let's first begin with the concept of a power function, though. This is going to be any function of the form f of x equals a times x to the power of n. A and n are both real numbers here, and a is considered your coefficient, n is considered your power, okay? So I want to look at the graphs of some various power functions really quickly, and let's try to look for some observations on the symmetry of those graphs, okay? So click this link here, we'll open it up. And you can see in box 1, I have a model for a power function, y equals a times x to the power of n. And then I have sliders that I can play around with the values of a and n. All right. I'm going to leave a as positive 1 right now. And let's focus primarily on the value of n. So right now, n is 2. So we're working with the power function y equals x squared. You're very familiar with this. It's a parabola. And I want you to notice there's symmetry in this graph with the y-axis, okay? If I make n 3, this is a cubic function, y equals x cubed. Notice the symmetry changes to being with the origin. Y equals x to the fourth looks a lot like a parabola again, back to symmetry with the y-axis. Y equals x to the fifth looks a lot like the cubic again, symmetries with the origin. Then here's 6, 7, 8, 9, and so forth, okay? So hopefully you're noticing that anytime the power is even for the power function, the graph is always going to be symmetric with the y-axis. And when we're odd for our power, the graph is symmetric with the origin. All right, now we talked a little bit about even and odd functions before from an algebraic perspective. So recall we said that an even function would mean that f of negative x would have to equal f of positive x, right? So for example, if I'm working with the power function of y equals x squared, where the power is an even number of 2, right? We know it doesn't matter what value I plug in for x, whether it's positive or negative, when I raise it to that even power, the result's always going to be a positive y value. So that's what gives us the symmetry with the y-axis, okay? On the flip side, for odd functions, we always said that f of negative x was equal to the negative of f of positive x. So if you think of something like y equals x cubed, basically what that notation is saying is that when I plug a positive value in for x, I'm going to get the opposite as if I plugged a negative value in for x, right? And that's because raising a positive number to an odd power results in a positive value, but raising in a negative number to an odd power results in a negative value. And that's where we get the symmetry with the origin, okay? Some other things that I think we were observing as we, played around with those sliders is that all the even powered functions, their graphs resembled a parabola, close to, y equals x squared, right? So it doesn't matter if it's x to the fourth, x to the sixth, x to the eighth, all of those graphs look a lot like a parabola. The only difference is they're a little bit steeper on their ends and a little bit flatter in the middle. And that's just based on, the larger that power is on x, of how the y value is going to change, okay? Similarly, all the odd power functions, they behaved a lot like y equals x cubed, our cubic function, with the same idea that the higher the power, the steeper the ends of the curve were, and the flatter they were near the origin, okay? So now let's explore the concept of end behavior. And this shouldn't be a new concept to you. You've definitely seen this a little bit in your algebra courses. But recall when we are talking about the end behavior of a function, we're saying, how's the graph of that function behaving near very small and very large values of x, okay? And we can generalize in behavior to the power and the sign of the coefficient on our variable, okay? So really it comes down to, is the power even or is the power odd, for first and foremost, okay? So let's consider just a basic even powered function of y equals 1x squared, right? So of course the power is even, and then that leading coefficient of a, it's positive 1, so it's a positive number. So we know that that graph behaves like this. And if that were x to the fourth or x to the sixth or anything, else with an even power, it would behave very similarly, right? So for that function, if I put in infinitely large values in for x, very large numbers in for x, after I raise them to the power that's even, they're going to stay positive values, right? They're going to be infinitely large as well. So I would say that f of x is approaching positive infinity. All right, so in terms of the graph, that's just focusing on the right side of the graph, that it's heading upward. As my x values are getting larger, so are my y values. Okay, as my x values get smaller, right, when I raise a negative number to an even power, it turns back to positive. So that means my y values would be approaching positive infinity. So that's focusing on the left side of the graph. Okay. Now let's keep the power even, but let's change the coefficient to being negative. So let's say we're working with y equals negative x squared. We know from our transformation rules that that's just going to reflect the graph across the x-axis, and now the parabola would be heading downward, right? So now as x is approaching positive infinity, f of x is approaching negative infinity. That's talking about this side of the curve heading downward. And then as x approaches negative infinity, f of x is approaching positive infinity. This side of the curve is heading downward. Okay. All right, now let's switch to the power being odd. So let's say we're working with y equals positive 1x cubed. We know that graph behaves something like this, and any other odd powered graph with a positive coefficient is going to behave similar to that, right? So as x is approaching positive infinity, as my x values get larger, so do my y values. That's talking about this side of the curve heading up. As x approaches negative infinity, f of x is approaching negative infinity. This side's going down, right? Because raising a negative number to an odd power results in a negative number. Okay? If I change the coefficient to being negative, so now let's say we've got y equals negative x cubed. Now my curve is going to behave something like this. And as x approaches positive infinity, f of x is going to approach negative infinity. We're heading down on this right side. As x approaches negative infinity, f of x approaches positive infinity, heading up on the left side. So again, these are generalizations that can be made based on the power on your variable, okay? And I want you to notice in general that for odd power functions, your end behaviors are always going in opposite directions, right? One side of the curve is always heading up while the other's heading down. But for even power functions, the end behavior is the same on both ends. It's either up on both sides or down on both sides, okay? Now let's move forward to the concept of a polynomial function, okay? Think of a polynomial function, it's just your power function with more terms added on to it, okay? So right here would be the power function. F of x equals a sub n times x to the power of n. And all I'm doing is adding more terms onto it whose powers on their variables are just smaller than that value of n, okay? So notice, based on the notations we're using here, we have a sub 1, a sub n minus 1, all the way down to a sub 1 and a sub 0. Those are just notations to represent the real number coefficients of each term in the function. And then n is your power on the first term there. Then we have n minus 1, next would be n minus 2, all the way down to an n value of 1 and an n value of 0. Those just represent non-negative integers, okay? Understand the domain for a polynomial function is always going to be the set of all real numbers, meaning I can plug any number in for x and I'll be able to get a result out for y. The degree of your polynomial function is going to be the largest power of x that appears. Okay, so that would be the value of n. This is your degree. Whatever the power is of the related power function, that's your degree. Okay. Now that would mean that if you're working with a constant polynomial function, your degree would have to be 0. Or what do I mean by a constant polynomial function? It would just be something like f of x equals a constant of 3, let's say. Isn't that the same as 3 times x to the 0 power? Right? Notice the power is 0 there. Okay. Now, one special situation here. Understand if you're working with the 0 polynomial function, which is just f of x equals 0, that's technically a constant function, but notice we're saying it's not assigned a degree. Reason is, think f of x equals 0, that really represents the x-axis, and it's a horizontal line. It doesn't have some of the same properties as the rest of our constant functions, so that's why we don't assign it a degree, okay? All right, now at this point, I'm going to give you an opportunity to practice this concept of n behavior as it relates to power functions and to polynomial functions, okay? But we kind of got to tie this all together first. Understand that the graph of a polynomial function will always resemble the graph of its power function, okay? So up here, this is the entire polynomial function, and then understand its related power function is just f of x equals a sub n times x to the power of n. So this theorem is stating that whatever the n behavior is of that power function, it's going to be the same n behavior for the overall polynomial function, right? So notice the example here. We have a cubic polynomial function graph. F of x equals x cubed minus 8x squared plus 16x. And notice that the n behavior of that curve is the same as the n behavior for f of x equals x cubed, right? As x is approaching positive infinity, f of x is approaching positive infinity. We're talking about this side of the curve. And then as x approaches negative infinity, f of x is approaching negative infinity, this side of the curve. Okay? So let's apply that theorem to this GeoGebra practice that's linked here. So what you're going to see here is we've got a polynomial functions graph given to us. And based on the graph, we need to determine whether the degree of that function is an even degree or an odd degree, and then whether the leading coefficient is positive or negative. Okay, so we can relate all of these scenarios back to one of the 4 scenarios right here. Okay, you can relate everything back. So if you get stuck at any point, just come back and look at this particular slide, all right? So let's go back and I'll just do a problem or two with you. Notice the n behavior on the left is down and on the right is up. Since it's going in opposite directions, I know I'm odd here. and then this would have to be a positive leading coefficient if it's down on the left and up on the right. So I'll hit check answer, and I'm good. Then I'll generate a new problem. Now you can't really see too much of the graph here, but based on what I can see, I can tell that on both ends we're heading up. So that tells me I'm even. And since they're both up, I'm a positive leading coefficient. Okay. So I want you to cycle through several problems on your own, work through those, check your answers until you feel you've got the concept down. Okay.